Hello, ladies and gentlemen. Welcome to Techtonic 2021. My name is Patrick Bangert. I'm the VP for Artificial Intelligence here at Samsung SDS America. And today I'm going to be telling you about how to efficiently and effectively develop medical AI imaging systems. Now, we're all used to talking about autonomous vehicles, which is the frontier of AI that is going to be coming up in the next few years. But from an AI perspective, that's really a solved problem. We know how to build autonomous vehicles. All that is really needed now is for them to be created and hit the streets, which will occur in the next few years. There's no more problem to solve here scientifically. So the next great AI frontier beyond that is what? In my personal opinion, it's going to be healthcare. It's really here where we see a confluence of a lot of outstanding research issues, and we see huge value that AI can provide. And it's particularly in medical imaging. Now, images like MRI, CT, ultrasound, X-ray, and so on and so forth are examples of medical images that are taken from you and me in order to help diagnose what might be wrong with us. In the Western industrialized world, about 5.5 billion such images are taken every year and analyzed by doctors manually. First of all, it takes time. If you take a biopsy and you wait for the results, it might take 6 weeks for you to get an answer back. And that, of course, delays the treatment that you might need to counteract that disease. Additionally, doctors have about a 70% chance of diagnosing you correctly, which means they have a 30% chance of getting it wrong, in which case, then, of course, you'll need a second opinion. So if you are ever diagnosed with anything serious, get a second opinion immediately. Contrasting, if we do this by artificial intelligence, we can do that diagnosis instantly, right after the image is taken, and with a much higher accuracy of 99% and higher to diagnose you correctly right away. Now, in order to allow artificial intelligence systems to be created that can take these diagnostics to the world, we need to supply them with example data. Now, not only the images themselves, but we need to attach a so-called label or annotation to that image, which is where the human domain experts, doctors, provide a drawing on top of the image that indicate where the disease is and what the disease is called. Having done that, we then, of course, need to train these artificial intelligence models in order to actually have them with the highest accuracy possible, which entails a variety of steps. And then ultimately, we take these models and deploy them so that doctors and hospitals around the world can use them. That aligns very well with the cloud-first strategy that is the new Samsung SDS business strategy going forward. We want to enable these models to live in the cloud so that anyone attached to the internet can access them and get their images analyzed. Now, what is this annotation thing? What you're looking at here is a CT scan of a human brain. At the far left here is the original image, which could be your brain or mine, hopefully not, because it has a brain tumor. On the lower left-hand corner, there's a brain tumor here. In the example of classification, the label is very simple. The entire image is put into a category, either a healthy category or a brain tumor category. So it's pretty easy and quick to establish that. Detection is the next level up, where we draw a rectangular bounding box around the aspect of the image that's of interest, in this case, the tumor that you can see on the lower left-hand corner. Instance segmentation is the next level, where we don't just draw a bounding box, we actually shade in the whole area that represents the tumor. And because that's, of course, a strange shape and not a circle or a rectangle, it takes a little more time to do that drawing. The most sophisticated kind of label is called semantic segmentation, where every pixel of the image requires to be labeled. In other words, we're drawing here on top of the entire image. And you can see in blue, the skull, in green, the normal brain, and in red, again, that corner that has the brain tumor in it. Producing a semantic segmentation label typically requires about 20 minutes for every labeler and every image. But I've told you that people get it wrong about 30% of the time, which means that every image needs to be labeled by more than one person. Typical industry standard at the moment is that 3 people independently label every image. So that means it takes an hour to label every image. 3 labelers, 20 minutes each. But if we simply look at the label, then it takes only about 20 seconds to judge whether or not that label is correct or not. So there is a big discrepancy between producing the label, which is a manual drawing process, and merely checking the label whether it makes sense or not. And that is, in fact, the basis of the business proposition around labeling and automating that process. Typically, data sets don't have a few images, but they might have hundreds of thousands or millions of images in them, which of course explodes the cost required to label them. So an example here, if we do 100,000 brain CT scans and label them with semantic segmentation labels, it would cost approximately $12 million and take about 19 people years to label it. If you use active learning, which I will illustrate in a few minutes, you can reduce that cost by 90% to just over $1 million or 2 person years. So you can see a dramatic reduction in cost and time required to provide these annotations if you use the right tool set to do so. Now, in any data set, there are some examples, some images that are very informative about the problem at hand. Other images contain less information because they are effectively duplicates. They're not exactly the same image, but they are so similar to the other images that they provide very little added value. So we need to select those images that have most information content, bring them to the top of the list of images to label, and of course, label them first. That technique is called active learning. And it's going to proceed in a fashion that I'll illustrate to you in a minute. For the time being, let's look at the results. The horizontal axis here illustrates how many images are being labeled in percent. At the left-hand side, we've labeled nothing, and proceeding to the right-hand side, we've labeled up to 1/2, 50% of the data set. The vertical axis gives you the accuracy growth over that time. In orange, you see the evolution of accuracy if we do this in a random order. And you can see that there is a trend for the accuracy to rise, of course, as more and more labels come in, but it is a haphazard growth and it is slow. The reason why the growth is so haphazard, going up and down, is because, of course, some images are constructive towards the problem that we're trying to solve, offering information about brain tumors and their location, whereas other images are destructive for the problem at hand because they don't offer any useful information for this. This might be brains that are diseased in a different way, not tumors. It might be brains that are not fully developed with children, or it might be all sorts of other problems with imaging techniques, not least of which is, of course, the artificial intelligence issue that every time you train an AI algorithm, there is a random initialization step, which means that these runs are not deterministic. And every time you run a model, there is a certain chance of it being of a lower accuracy. And so you see generally an up and down as you go through a data set. If you label the images in the correct order, in the active learning order, in the blue curve here, you see the accuracy shoot up very quickly. And after about 5 or 6% of the data set is labeled, we hit a near maximum accuracy. You can see if we label more images than that, the accuracy does change a little bit, but by an insignificant amount. So at that point, at the 5 to 6% labeled point, we can stop doing manual labeling and we can label the rest automatically and then merely check whether they are okay or not. And that's where this 20-minute versus 20 seconds game comes in that I was talking about. You inject the 20 minutes per image with the first 5%, and after that, you stop doing that. You merely check at 20 seconds an image. And that's the aspect that can lower the $12 million investment to a $1 million investment instead by automating the process. Of course, those are examples, and in real life data sets, the amount of cost could be higher or lower depending on the amount of images available. How does this work practically? What's the process like? Well, here's a high-level diagram of how active learning works. We start at the top left with an unlabeled set of images. Then we perform an unsupervised training exercise to learn the structure of that data set. It effectively clusters the data set or provides some kind of computation to detect similarity and differences between images, leading to a structured model that shows us then how different images are, and then we pick from most different images a first batch, the first small set of images to be labeled. If we already have a model from a very similar application available, we can use that as a pre-label model to supply pre-labels before the manual labeling process begins. If we don't have a similar model yet, then we cannot do that step. So that's kind of optional. The human labeling team comes to bear now and actually labels those images in that small batch that have been chosen. These are then provided to the active learning model itself, which learns what it can. It doesn't learn yet how to diagnose the disease, but it attempts to learn which images offer the most amount of value, which could be assisted by an unsupervised model trained previously as well at that point. The remaining unlabeled data is then used by the model to provide a score for every image. And an acquisition function is applied to choose from the list of unlabeled data the ones that are most likely to yield added value. And that's really the heart of the intelligence in the active learning process, this acquisition function that we need to choose the right next batch. And I'll go into that more detail in a minute. At every iteration, we choose, is the accuracy of the model good enough yet or not? If not, of course, we continue for one more loop. If it is good enough, then we can exit this loop. We can apply the active learning model to all of the data and have the reviewing team, typically the same people as the labeling team, review and check all of these automatically produced labels, and then end up eventually with a fully labeled and humanly verified set of data that we can provide to the proper AI training methodology that produces the diagnostic model that we can apply in real life practice. So, of course, we didn't invent all of this on our own or develop the software independently. This is based on a number of tools that are listed on the right-hand side here that enable us to take these methods and these ideas and put them into practical reality running on real computers. And so everything I'm about to tell you is available as real software ready for productive use and verified by real customers. There are 5 areas here in this chain where Samsung SDS America has provided added value by our research, and we've improved the overall efficacy of this methodology. We are currently about twice as efficient as the state of the art, both the state of the art in academic research as well as the state of the art available in commercial software. If you're interested in any of the details, the mathematical minutiae of how to do this, we've published our methods in technical papers that are available in journals and conferences. If you want to have access to them, please write to me and I will give you the literature. We also have applied for patents for these methods. So in the next few months, I hope that we will hold that intellectual property in the form of a patent. Let me illustrate a couple of methods that are very interesting. First of all, the acquisition function that I said was the heart of the process. We have designed a new acquisition function. We call it BABA. It's based on Bayesian statistics. Now, Bayesian statistics is a form of doing statistics which has become very popular in artificial intelligence and machine learning because it's a kind of evolutionary process. You begin with what's called a prior distribution, prior meaning before. So before you have any more detailed knowledge, you come up with an estimate. It's usually the uniform distribution. In our case, that means every unlabeled image is regarded to be informative with the same likelihood. But we gain knowledge. We gain knowledge in a variety of ways. We gain knowledge by that structure learning that comes in from the beginning. We get knowledge by the labeling team providing labels through the loops. And so at every iteration, knowledge is being externally introduced into the data set, which means the prior distribution can be updated to yield a posterior distribution, a posterior meaning after the injection of human knowledge, the distribution is updated and becomes more accurate. After only a few iterations, maybe 2 or 3 iterations of the active learning loop, the knowledge is sufficient for us to have a pretty good statistical distribution via Bayesian statistics over the unlabeled data set, allowing us to choose more accurately the next images to be labeled. And we see the performance here very well in the diagram on the left. Again, the horizontal axis is the number of images being labeled, and the vertical axis, the accuracy. In purple, you see the BABA, the new method that we've invented, which clearly yields a faster growth in accuracy and in a more robust and stable manner than competing methods. The blue dotted line here is the current state of the art, which is a method called BALD, and compared to here in beige, the random order, where there is no special acquisition function, and we simply label images in a random order. You see very clearly that our new method is able to achieve a higher accuracy faster, which is ultimately the point. On top of that, however, BABA is even much, much cheaper to implement from a computational resources point of view, because it's currently the only method that does not require pairwise computations. A pairwise computation is where you take 2 images and you compare them to each other. Now, if you have hundreds of thousands of images, if you need to do pairwise computations, that's going to take a very long time. It doesn't scale well with the size of the data set. BABA, however, doesn't need to do that, and so it scales very well with an increasing data set. It's also very robust. As you can see very well, the increase is very stable without any dips in it. So this new acquisition function allows us to be more efficient computationally, more effective scientifically, and achieve a high accuracy very quickly. I've shown in the beginning that with semantic segmentation, you typically need to label the entire image. Every pixel needs to belong to some category. And we looked at the brain with the skull and the brain and the tumor, all of which were colored in by, of course, a person. It turns out that that's not, strictly speaking, necessary. If you only label 10 or 20 pixels in a single image, that is typically enough to produce an automatic semantic segmentation for the entire image. Now, if you think just a regular Samsung mobile phone can take several million pixel images, a medical image is typically very, very large indeed. And so if you label only 10 or 20 pixels, we're talking about labeling a very small amount of that image. Nonetheless, it is sufficient to do that. And by combining both that BABA acquisition function I just talked about with pixel-based labeling, we can again achieve a much, much faster labeling accuracy here. And again, the image shows in red the growth in accuracy with pixel-based BABA, as opposed to the random order labeling in blue, or the pixel-based method of labeling without using the BABA acquisition function in gray. So again, we see the combination of BABA with pixel labeling beating the other algorithms. In fact, in orange, the horizontal line on top, that is the maximum accuracy achievable for that particular data set. And so we see that our BABA method achieves that maximum accuracy very, very quickly. And so you see that there is benefit not only in the acquisition function, but in pixel-based labeling. After only 0.4%, less than 1% of the data has been labeled, we already achieve maximum accuracy. The other 99.6% of the data set are not necessary to get there. And so again, the methodology reduces dramatically the amount of manual effort flowing into this process. In the overview slide, I talked about there being an unsupervised initial step, and maybe there being a pre-label model at the side, right? This is where PatchNet comes in. PatchNet is an unsupervised method to figure out where are the objects of interest in an image. You see at the top here 2 images with people, either faces or whole bodies in them, with the nice bounding boxes around them. This is something that you might expect to see from an automotive type of data set. Hey, we find the people, these are obstacles. But in fact, these rectangles were not provided by a human labeling team. They weren't even provided by a normally trained supervised methodology. This is the outcome of an unsupervised discovery process. The way it works is illustrated at the bottom of the picture here, where a random set of patches, rectangular bounding boxes, are being put on an image in a random fashion, and an analysis is done between the pixels inside that box versus the pixels outside of the box. We try to maximize the differences, maximize the contrast between inside and outside of the box. And through that method, the algorithm learns what objects are most different from the background. Now, most images, both in the real world and in medicine, have a rather distinctive object or thing, for the lack of a better word, that is quite visible and different from a mostly uniform background. And this method is able to automatically observe this and bring it out to the forefront for everyone to see. So we can see this is an automated object discovery, which doesn't require any labels, and therefore can again reduce the amount of human labeling that we need to do. We've done some of this work together with real medical institutions that are our customers. So Intuitive Surgical and Philips are both manufacturers of medical devices, and the City of Hope is one of the largest cancer centers in the United States. They've worked with us on numerous examples to actually put this to the test. So we've done this on X-rays to detect COVID-19, which is something I talked about at Techtonic last year. And then we've augmented this by whole slide images, which are the result of taking a biopsy of human tissue and putting it underneath the microscope, in this case to detect breast cancer. We've done this to intravascular ultrasound, which is where an ultrasound sensor is inserted into your blood vessels to measure the thickness of the available blood vessel to detect heart disease, and place a stent in your blood veins to open them up and to prevent you from having a heart attack. We've applied it to colonoscopy, where the aim is to detect whether or not you have colon cancer, to MRI scans, where we're trying to detect a brain tumor, and also to angiography, where an X-ray is taken of your blood vessels, again with an aim to look at the risk for heart attack and stroke. In each of these particular examples, we've applied AutoLabel, our automated technology, to label medical images, and we found an over 90% efficiency improvement, can reduce the amount of human labeling effort and therefore boost not only the financial performance of these models, but the amount of time that it takes to bring that model to the market. So very significant value demonstrated in all of these cases. And in fact, Intuitive Surgical has since become a paying customer, so that our AutoLabel product is not only ready scientifically, it's on the market up for sale. Now, the plan in the future, in the next months and years, is a three-pillared plan. First of all, we plan to continue our history of scientific excellence, where we develop the methods of active learning and modeling for medical data sets. We're trying to make things better that we already have, plus include some features that are needed for the medical industry, in particular data about 3D scanning, which would be slices of 2D images through human tissue to arrive at a three-dimensional holistic model of an organ or a body part. And also multimodal data, which is a combination of an image and some text, the text that the doctor might have written in the consultation with the patient. And we have a few partners in this research, Stanford School of Medicine and Harvard Medical School, for instance, that are participating with us in doing excellent research, and McGraw-Hill, the publishing company, that has a lot of scientific data available. Secondly, we're moving forward with AutoLabel and the Bredix AI Accelerator as a tools business, where we're supplying these tools to partners to annotate their data sets more efficiently, to get models trained and to deploy them. And we're working with a number of collaborators here and customers who are willing to make use of these technologies to develop medical models of their own right. Finally, what we really want to do in the long term is to develop models to which Samsung SDS has the intellectual property, and to maintain these models in the cloud in accordance to the corporate strategy of cloud first, where we can then provide that knowledge to hospitals and doctors to use for diagnostic purposes in real medical applications with patients. And here we're working with some of the partners that have already started working with healthcare in the cloud, IBM Watson being one, AWS, the Edge Healthcare team. We're working with Oracle Cloud, NVIDIA, and NetApp as well to provide these models in an efficient and structured way at scale in the cloud. Thank you very much for your attention in this talk. Again, I would have loved to be there in person with you, but unfortunately we had to do this virtually for the second time this year. Please do feel free to reach out to me on LinkedIn or otherwise. I'm very happy to answer your questions after the event or to supply you with some of our published material. And in case you have any questions right now, I'm more than happy to answer them. Thank you.